Have you ever found yourself just swimming in data? You've got an ocean of spreadsheets or images, and you just wish you could filter out all the noise and find the, like, 3 or 4 things that really matter.
That exact feeling of overload is pretty much the core challenge we're tackling in this deep dive.
I'm glad it's not just me.
No, not at all. We're exploring sparse approximation theory, which is also known as sparse representation. The whole concept is actually quite elegant. It asks, how do we take a really complex signal, something with maybe thousands of components,
Right.
and explain it using the smallest possible number of essential elements?
Okay, let's unpack that a bit. So there's this algebraic system, 6 donkers, d alpha. Help me break that down.
Right. So think of $6 as that complex signal, that huge data set you're trying to understand.
Oh, ocean of data.
Your ocean of data. And dollars is what we call the dictionary. It's basically a collection of all the fundamental building blocks or atoms that are available to describe $6.
And our mission then is to find alpha.
Exactly. We need to find the sparse representation alpha. One of the sources we looked at had a great analogy called $6 a molecule that's composed of just a few fundamental atoms taken from that dictionary dollar.
So finding a sparse solution means finding an alpha with the fewest non-zero values, the fewest atoms.
You got it. We want to find the exact count of non-zero entries in alpha, which mathematically means minimizing what's called the Elver-Dollar pseudo-norm.
And that's where we hit a wall, right? Because just counting them, as simple as that sounds, is actually incredibly difficult. It's NP hard.
Yeah, NP hard basically means that for any real-world data set of significant size, finding that perfect exact solution would take, well, more computing time than the universe is left.
So it's computationally impossible.
Pretty much. So researchers had to get clever. They had to develop approximation algorithms.
And that's the turning point, moving from this impossible problem to a clever solution. What was the first big breakthrough?
That would be convex relaxation, which led to an algorithm called basis pursuit, or BP. The idea is, since we can't actually count the non-zero elements using $dollars, they substituted it with a much easier problem, minimizing the dollar norm.
Wait, hold on. You're substituting a sum of absolute values, the dollar norm, for a strict count of elements. Why on earth does that work?
It's a great question. It works because the $dollar norm has this amazing mathematical property where it naturally encourages the coefficients in AlphaTold to go exactly to 0. Other norms, like the common $2, would just push them to be very small, but not 0.
Ah, I see. So that substitution is what makes it solvable.
Yes, it turns the problem into something that can be handled efficiently with standard linear programming solvers.
Okay, that makes sense. But if basis pursuit gives you this globally guaranteed solution, why do people still use the other approach, the greedy techniques?
Speed. Sometimes speed is just more important than having the most rigorous mathematical proof of optimality. Greedy methods like matching pursuit, and especially its improved version, orthogonal matching pursuit, or OMP, are built to be extremely fast.
How do they work?
They work iteratively. So at each step, they just pick the single best atom from the dictionary dollars that fits the signal.
And I'm guessing that orthogonal part in OMP is the key improvement.
Absolutely. OMP is crucial because after it finds a new atom, it performs a least squares update. This step ensures that the residual, the part of the signal we haven't explained yet, is mathematically orthogonal to all the atoms we've already chosen.
So it prevents the algorithm from just picking the same things over and over.
Exactly. It makes sure there's a clean, fast path to the best possible fit. And this leads to the really encouraging part of this field, the huge breakthrough you mentioned, the theoretical guarantee.
Tell me about that.
Under some specific, pretty mild conditions on the dictionary dollar, it turns out these approximation algorithms, both BP and OMP, are mathematically proven to find the unique, perfectly sparsest solution.
So what was once an impossible counting problem is now a solvable optimization problem.
That's it. A solved problem.
This deep dive into complex algorithms and just the sheer ingenuity required to solve these challenges, it really reminds us that leveraging smart technology is key to progress. This discussion is sponsored by Embersilk. If you need help with AI training, automation integration, or software development, Embersilk helps businesses and individuals uncover where AI agents could make the most impact. Check them out at embersilk.com for all your AI needs.
And when you look at the results, this theory is providing state-of-the-art results across so many fields: signal and image processing, data mining, medical imaging.
Can you give us a really tangible example of where this has made a difference?
Sure. A great one is in medical imaging, specifically with MRI scans. Sparse coding lets us acquire those images much, much faster. Because we know the underlying image has a sparse representation, we actually need far fewer measurements during the scan itself.
Hmm.
This dramatically speeds up the process for patients. It's a direct quality of life upgrade powered by math.
That is a perfect illustration. Intelligent simplification in action. And the field is still growing, right? It's moving beyond just single signals. I read about structured sparsity,
Yes, where the algorithms are designed to pick entire groups of atoms together. And also collaborative or joint sparse coding.
which is four.
That's for analyzing whole sets of related signals together, forcing them to share the same underlying atoms. It's crucial for tasks like face recognition across multiple different images, for instance.
So if this whole theory is about finding the simplest possible representation of something complex, what does that mean for the future?
What's really fascinating is the tight connection that recent work is showing between sparse representation and deep learning. The ability to boil this incredibly complex data down to just a few critical components means we can create AI systems that are not only more efficient and powerful, but also, and this is key, more understandable.
More interpretable.
Exactly. The future of data science really does lie in this kind of intelligent simplification. It's what will lead us to clearer insights and much faster solutions.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.